Next presenter is Dr. Omar Alajarmeh. The title of the presentation is Composite Durability and Degradation Prediction using Arrhenius model, sorry. So Dr. Omar is a senior researcher and teaching fellow specializing in fiber composite manufacturing and their applications, including their short and long-term behavior. So Omar, the floor is for you. Let me just stop sharing and you can share your screen.
Thank you, Hadi, for the introduction, and thanks all of you guys for attending those seminars. It's a great opportunity for all of us to share the knowledge, and thanks, Molly, for that initiative. Let me start with sharing my screen. Do you see my screen, Hadi?
Yes.
Yep. All good. So let me start with our topic today on composite material durability and degradation prediction using Arrhenius model. I selected that to be very specific because, again, actually this, if you would like to go in deep with the degradation mechanisms and durability, it needs a few books to cover. But I have selected some examples and some projects that we have done previously on composite durability and degradation. Let me start with acknowledging of the First Nation and paying the deep respect for elders past and present. So generally speaking, if we want to identify durability, what durability means, and the straightforward definition will be the ability of that material to keep resisting mechanical, mechanical and environmental loads, and including any environmental attacks like chemical attacks, physical aging, and weathering, and all of these things over a period of time. So to understand how a composite material can resist that load, or let's say how can that sustain for that amount of time, because it's a major let's say question now in the market, how long the composite will last for. Okay, it's good to understand what are these let's say conditions that can affect the service life of the composite. And I listed that as general forms of aging for composites. And we can say that it's chemical aging, sorry, chemical aging, mechanical aging, and physical aging. Yes, it's not a sudden impact on the composite, but it's a time-based impact on those composites. So if you have a look on the figure here, you will see how that will go in deep to the lamina level, from the laminate level to the ply level, having small, let's say, micro cracks, or let's say localized debonding between the fibers and the matrix, maybe micro cracks in the matrix, and even, let's say, changing the behavior, or let's say the chemical form of the matrix. Starting from the first factor, which is a critical factor of aging. We are talking about chemical aging. And chemical aging is occurring after long aging duration and causing decrement in properties of the polymer and changing in the chain and cross-linking of the polymer. And that is changing the whole properties, the whole properties of the polymer. And the form of the chemical aging is you can have thermal as a form of chemical aging. You can have thermo-oxidization or aging, and hydrolytic aging, and all of that related to chemical aging. So for thermal aging, what we mean by thermal aging is more about molecular deterioration that coming from overheating. And overheating, what we mean by overheating is a temperature that is close to TG or over that. So what is the cause afterwards? What is the features that you can see from the thermal aging? One is reduction in ductility and seeing some brittlity in the polymer. And the second thing is more about a color change. So you will start to see a yellowish side of the polymer. Cracking, micro crackings, and debonding between the fibers and the filaments and the polymer. And you can have, let's say, a reduction in the physical properties, like increase in the moisture absorption and all of these things. Thermo-oxidization is fairly, let's say, common, which is more about, let's say, if the polymer that you have a radical-free linkage, so that is susceptible to react with the oxygen. And again, actually, it's a loop reaction with the time that can end up with loss of moisture, reduction in the molecular weight, and cut in the cross-linking, increase in the glass transition temperature, which is somehow or sometime or some of the aging, let's say, aging test that we have done revealed an increase in the TG of the polymer, and mechanical properties, which a little bit toughness, reduction in toughness, reduction in stiffness a little bit, and reduction in the strength. Going for physical aging, so physical aging, again, it's a time dependent. So all of them are time dependent aging, and but it can affect more about, let's say, amorphous and semi-crystalline polymers with no modification of the polymer chemical structure, which is unlike the chemical aging. So a general form of those physical aging, which is a hydrothermal or hygrothermal, some people call it, and weathering aging. Weathering aging is mainly the UV. Sorry. For hydrothermal, so hydrothermal is a combined process between subjecting the sample or the polymer to a temperature as well as moisture at the same time. And that temperature should be less than TG. And less than TG is to the level that temperature will not change or will not intercept with the thermal aging. And again, actually, what is the feature of the hygrothermal or hydrothermal aging? You will see a little bit swelling in the polymer, changing the moisture absorption or the absorption capacity, and seeing something called the plasticization of the polymer, where the water is infused in the polymer and the temperature increase the infusion of the water into the polymer. We have weathering, and weathering is the UV, which is sometimes actually subjecting all the composites that exposed to sunlight. And again, actually, for weathering, it's intercept with thermo-oxidization, where the weather or the energy coming from the wavelength of the light break some of the cross-linking and help for the oxygen to react again with the polymer and do or let's say feedback on chemical aging. Finally, mechanical aging is mainly known by creep aging and fatigue aging, and both are, let's say, time-dependent aging. So it's a type of load at the end of the day, but it's again actually it decide on durability of the composite. For example, for creep aging, it's a permanent deformation in the composite in the polymer material that will not be able, so the material will not be able to retain the original shape afterwards. However, the fatigue aging is more about, let's say, a cyclic load or repetitive load that can create micro cracks in the polymer, which can be developed afterwards into a final failure or separation between the fibers and polymer. So just to focus more on, accelerated agent, or came from the environmental impact or from the environmental effect, which is more about the physical effect or the physical aging. How we can, which is a general question, how we can make those accelerated agents, or how I can simulate the polymer subjected to aging in the reality, how I can simulate that in the lab. And there is some points here where we used in the lab to simulate the exact environmental impact, let's say in reality. So one of the tests that we are adopting is more about increasing the exposure temperature to accelerate the water diffusion, and this is hygrothermal. Increasing the concentration of the chemical or compound that will help in degrading the polymers is more about, let's say, alkaline solutions and acid solutions. Extreme temperature cycling to induce cracking and delamination, and this is more about freezing and thawing for the environments that have high temperature and low temperature. We have wavelength to accelerate. Photodegradation is more about UV. So you can actually control the UV energy using some lamps and give different energy wave for that polymer to react or to accelerate the degradation. Increase the humidity, increase loads, and condensation of cycles, which is more about, let's say, mechanical testing. So you can actually change the creep load, the level of load. You can change in fatigue. You can change the stress ratio. You can change the bond of, or the bound, the upper bound and lower bound of fatigue testing. So after doing testing, there is a simulation or modeling for this type of aging, and mainly we are looking for a function for modifying the parameter with the time. So this is an example on that is mechanical properties, or the aging came from mechanical properties. For example, in that function, which is x to the power n, is more about creep and fatigue. If you change the stress ratio, if you change the level of load, you will get this function suits those type of aging. However, if you are looking for a function for the rate of variation of the parameter with a level of degrading agent, and this is when we are looking for physical and chemical aging. So we need temperature, and we need time with the temperature, and we need something called activation energy, which will go after this slide. So a part of that, we are focusing more on Arrhenius model as a model that can describe some of the thermal, hygrothermal, and weathering aging of the composite material. So what's Arrhenius model? It's more about a formula for the temperature dependence of reaction rates. So you have a reaction rate, and the temperature is one of the controller on that reaction rate. So as you see from the formula here, K is the reaction rate. A is more about the constant based on the material. And you have exponential of minus EA, which is the activation energy. R is the gas constant, 8.13, and T is the temperature or the service temperature. And if you have, or if you take the logarithmic base on that equation, you will end up with a linear equation, which is log 1 over K, it's the time, and minus EA over R, which is the activation energy, and here is playing as a slope. If you imagine that equation as y equal ax plus b, and these are the terms of that linear equation. So the slope here is the activation energy, which is the thing that we are looking for when we analyze how the composite is degrading and what is the degradation rate of the composite. I'll go through an example which make the thing easy and quick to understand. Is more about a GFRP in alkaline solution. So GFRP, what we have done previously, we have taken a reinforcing bar, GFRP bar, and we cut that into small length. And the target for us was to test that into under interlaminar shear test, which is a 3-point bending. So what we have done, we put that bar in alkaline solution for different durations and different temperature. So we have put that in 28 days, 56 days, and 112 days. In room temperature, 23, in 60 degrees, in 80 degrees. And we start testing those bars after these points. We have selected 3 to 5 bars to be tested to represent one dot point. So the reference is tested at the beginning, and then we start to notice that, okay, there is a reduction in the strength with the period and reduction in the strength when we increase the temperature. And here on the left hand or the right hand side, you will see strength retention. Strength retention means we have divided these values in the table on the reference strength of those bars, and we have seen that there is a logarithmic relationship of these test results with the time. So the question was, what will be the service life of the bar? Okay, for how much that reduction will be, and what will be the reduction at the end of the day. So what we have done is we went through a calculation for the activation energy and the time shift factor. What I mean by that, if you go back to the figure, you will see equations. Y equal that number multiplied by ln x, or ln the time, plus a factor, or the intercept. So we pick up all of these three equations, which everyone is related to a different temperature. So for the first equation, we reverse the calculation to say, okay, how many time or how many days I need to reach 90% as strength retention, and how many days I need to reach 80% and 70% and 60%. Same as for the other relationships, which is at 60 and 80. So the outcome of that was plotted in X and Y according to the equation that we have seen before 2 slides, which is the linear equation. The linear equation expressing on activation energy as the slope of the linear line. So from the slope here, or from plotting these relationships, we have found that activation energy is the slope of those numbers, and we got that averaged at 2.26. So different material, different average, different material, different activation energy. So once we got the activation energy, we now look to have the shift factor. Shift factor means if your material is tested at room temperature and to degrade that material into a certain level, to degrade, for example, polymer, to reach 60% of the original strength at room temperature, you might need 1 year. But to accelerate that degradation, there is something called time shift factor. So you need to apply higher energy or higher temperature to accelerate that process. So, and this is what we call time shift factor, TSF. And from the TSF here, it's a relationship that you need or you have to have the activation energy of the material and the reference temperature and the target temperature. So for example here, if you are changing from temperature, room temperature to 80, the time shift factor is 3.41. What that means? That means if you tested or you aging your material at 80 degrees, that will reduce 3.41 the duration that you are testing if you are testing that at 23 degrees or at room temperature. So once we have that time shift factor, we go again to the table that we previously constructed, and we multiplied all the other temperature with their relative time shift factor. And this process called developing a master curve. Master curve is a curve that have a lot of dot points, representative point, to get a reliable relationship that can give me an indication on the service life of the polymer. So once I have that master curve, I take that the function that I'm getting from the regression of those dot points, and I correlate it into a service life up to the target, let's say, years that you are looking for. For example, in our project, it was 100-year service life. And again, actually, how we do that, you will take the function, you will start to change x axis, okay, or x values to get the y values. So the strength retention in percentage after 100 year, in our case, it was around 52%. So that is giving a solid evidence on somehow how those type of polymers are reacting against environmental, let's say, agents. And again, this is one of the example that you can actually do infinite number of other examples based on different polymer composition and different even, let's say, loading configuration. So that the example that we have given here is more about interlaminar shear strength, but you can repeat the same thing for flexure. You can repeat the same thing for compression and transverse shear and tensile as well. So for this thing, I'll stop until here, and I'll come all the questions if you have any. Thanks.